today, yesterday we had this kind of introduction of, radiometry, apparent optical properties, but that was basically all theoretical. Then you moved into radiative transfer using hydrolite and doing all sorts. That's kind of theoretical as well. So this lecture this morning is about the measurement uncertainties, or in general, the uncertainties we have when we try to derive this, measure these radiometric quantities and then derive the apparent optical properties from that. So there will be some of the slides will be presented by Matt, who is sitting with us today. So probably many of you have already seen this. It's just okay. Should I stop this one then? Okay, thank you. We can be moving just a bit more. So that's just a simple way to remind what's precision and accuracy and how both are actually considered to determine these uncertainties. So you have these few targets, and the yellow stars are supposed to be the number of tries that you have been doing to reach the target. And when they are all on the right, on the top right graph, so this one, sorry. Okay, they're all well centered on the targets, and they are all grouped. So they are all centered there, so it means you have been accurate, because if you derive the value here, that's indeed the center value. And you have been very precise, because all of your tries have been basically grouped on the same value. If you move to the top left, you are still quite precise, because all your tries are on the same place, but you're completely off the real value, so you have a low accuracy. If you go down on the bottom left, you have now a low precision, because you're going to end up at very different place on the target. But you can see, if you would have read all that stuff, well, basically you would get to the right value, so you have still a good accuracy. And finally, on the bottom right, all over the place, and even if you average all these values, you will be completely off the target value. So it's low accuracy, low precision. And in that case, high uncertainty, and in the other case, on the left, high uncertainty. Yes, no, sorry. It's high uncertainty on the two. And the other way to represent this is that, when you make a number of measurements, you may have a distribution of the values, like this normal curve or Gaussian curve, and the red line is supposed to be the value you would like to get at the end, and how far you are from this true value is your error, and how wide this distribution of your measurements is determined the uncertainty. So that's just a quick reminder about the what makes this uncertainty that we're going to discuss in the next hour or so. And if we generally speak about uncertainties, is because, well, actually the true value, we don't really necessarily know exactly what it is as well. So it's always a matter of, comparing values with their own uncertainties, like, you compare a satellite value with an in-situ measurement. Well, none of them might be really giving you a truth value, but they all have their uncertainties, and how these uncertainties are, how large or small they are, will make the comparison meaningful or not. Okay, why do we care about all that stuff? Well, that's a bit a complicated thing to do. So, of course, you want to use all this data to do good science. If you have no idea of the uncertainty of your measurements, it's hard to make any conclusions. For instance, for those who work on long-term time series, to look at changes in the ocean color record over 20 or 30 years, you need to have an idea of the uncertainty in your measurements if you want to conclude on any long-term trend, for instance. When it comes to the field measurement that we do, well, space agency want to get this for validation of their satellite sensors. But again, now they really want you to provide the data with an uncertainty, so they know that they can use indeed the data for validation, or maybe, well, your data is just too bad and with too large uncertainties and won't be used for any of this validation work. You want to be useful as well for any other potential user of the data, and that might be completely out of the research arena. When you provide in situ or remote sensing product, I don't know, to the fisheries industry, to people looking at water quality, environment agencies, and so on, they are supposed to use this to make some decisions about, the water quality is bad, people should no longer go to the beach or whatever. Well, again, knowing the uncertainty of the data is very important in that case. But the last point actually is what I just said before about the science. Be able to quantify long-term trends in satellite ocean color radiometry. That's one of the goals we have at the moment, because we have accumulated 25, nearly soon 30 years of ocean color data from space. It starts to be quite a long record, and many people are trying to figure out what this record is telling us about the long-term changes. But again, that's a lot about knowing the uncertainties. So uncertainties, as it's written here, that's all about metrology, but as well deployment protocols and data processing techniques. And we are going to look a bit at these three important components of, or important source of uncertainties, if you want. There is a reference on this slide that's called this Guide to the Expression of Uncertainty in Measurements, or the GUM. You have the full address there. If you go there, you will be maybe a bit overwhelmed by this document. It's a huge document. It's going through all of these things in very detail. So, but if you are, interested to understand a bit more, that's definitely one of the main sources. So let's start with a simple example. Okay, you probably all know when you have on the left typical profiles of the upwelling radiance and downward irradiance in the water column that you can get from a free fall radiometer, for instance. And from the LU-Z, so the profile of the upwelling radiance, we want to extrapolate to the surface and derive the water-leaving radiance. And the equation is that one. So you have your LU at a given depth, the diffusion attenuation coefficient for the upwelling radiance, and then that will get you to the LU 0 minus, so just below the surface. And then you have to cross the water-air interface, and you have this reflection coefficient and the index of refraction. So it's kind of a simple equation to go from LU bed, so the profile of the radiance, to the LW. Well, is it actually that simple? So we're going to have a look at these relatively short equations and where the uncertainties come from in this. And to do this, we take a simple example of a buoy where you have measurements of this LU at just two depths, okay? You don't have the full profile, like when you do use a profiling radiometer, but there are quite a number of systems in the sea which are doing this, measuring the LU at two, maybe three depths, and using this to extrapolate to the surface. So that's the example of this boussole buoy that has been deployed for many years in the Mediterranean Sea. And this one had a measurement at, roughly speaking, 4 meter depth, and another one at 9, okay? And the downward irradiance above the surface was measured at plus 4 meters above the sea level. So I have put again the equation at the bottom. LW equal 1 minus rho divided by the square of the refractive indices. LU at Z1, which is going to be one of these depths of measurements, and the exponential of minus K well, that should not be minus, by the way, on this one, but anyway, depending on the times the depth. Okay, still simple. Now, if we expand what is making this LU measurements at the first depth, that one. Oops, no, that's the other way. Okay, let's expand this a bit. Oops, it's becoming a bit more complicated. Okay, well, don't be afraid by this. It's just okay. Look at the the equation is which is here. That's multiplication of many terms. The first one is this S here. It's just coming from here. So what is it? Your instrument is giving you a digital number. You know, the instrument is collecting light and coding this on number of bits, and you have your digital signal. You may want to first remove the dark value. The dark value is the one you get if you put a cap on the instrument. The instrument is not receiving any light. There will still be kind of a noisy dark signal, and you don't want to include this in your data, so you remove it. So that's the first thing. And well, there is a bit of noise in all these two measurements. So that's the first source of variability and uncertainty. Then you multiply this value by a calibration coefficient, which is going to transform this into radians in watt per square meter per steradian and per nanometer, for instance. But then, you know, there are a number of coefficients that are applied as well, and which are supposed to correct or to take into account a number of instrument-specific effects and corrections. So one might be about the stability of this calibration coefficient over time. The second one might be something about the spectral calibration of your instrument. You know, you think you're getting maybe a data at 443 nanometer, maybe it's 443.2, whatever. You know, there is always a bit of spectral uncertainty. The linearity of your sensor, we mentioned this briefly yesterday, and so on. Temperature effect, stray light that may happen in the instrument, and so on, and as well some corrections that you may want to apply, like the one in blue at the end, is the correction for self-shading. You probably know what is self-shading. It's basically when you have an instrument looking down in the water, collecting radiance, the instrument has some physical size, so it's blocking light in some direction, so that's modifying a bit the light field. So you have some error because of this, and you may want to correct for this. And to do this, you might need a model. Maybe you have been deriving some correction from the radiative transfer calculations, but this calculation will need to know about the absorption and will need to know about the sun-zenith angle. So that's all the blue box on the top here. Okay, I can stop here. I don't need to go into detail of all these things, but you can already feel and understand that this simple LU value you get from your instrument, there are a number of uncertainty sources to it that can make it, you know, quite inaccurate at the end. Okay. So that's for just the LU measurement at one depth. But then, well, you have a KU in there. So KU is using the two values at the two depths to calculate and extrapolate to the above the surface. So in that case, of course, you will have, well, again, the same thing for the LU at the other depths, okay? All sort of, but then you have as well the two measurement depths. Okay, do you know them very well? Or maybe not. That might be because, I don't know, you have a pressure sensor to tell you what's the depth of this instrument, but maybe the pressure sensor has its own uncertainty. Maybe when you have measured the distance between the two sensors, they are fixed on the buoy. Well, maybe you have measured it very well, but maybe you did some error on this measurement as well. So again, I guess you can start to feel the sort of inaccuracies that can be brought into the system. And finally, you have the rho coefficient, which is the Fresnel reflection. So that's function of the wind speed and the angle. again, that's a model, that's a value, and you can imagine that maybe depending on the angular resolution you use, you might end up with some uncertainty on that value. And finally, the refractive index, as you know, it's depending on salinity, might even depend a bit on the temperature. So whether you use a constant value or you try to make it a bit spectral or whatever. But again, that's bringing a bit of uncertainty in the system. So, well, you see, we started from a very simple equation, and we already see that if we want to include all this uncertainty, that's going to be a bit complicated. Okay, let's be a bit more positive. Many of them might be extremely small. It's fine, but it's not only the uncertainty on any given parameter you have in this complicated graph, but what we call the sensitivity coefficient associated to it. You might have a coefficient which is very not well known because it's hard to determine and you have a large uncertainty. But maybe its impact actually on the final value is extremely small, so you don't really care. There might be other parameters in this graph that you can determine relatively well. They have a low uncertainty, but they have a very high impact as well on the final result. So on that one, the uncertainty, you really want to make it as small as possible. Okay, this thing is discussed in the paper, which is included in this slide as well. Okay, so the thing is you need to combine this uncertainty because what you are interested in at the end is you want the uncertainty on LW, on the final product. So quite often what is done is just to use the quadratic sum of this uncertainty. That's what is expressed here. It's generally okay when these different source of uncertainties are independent and random, okay? And there are slightly different ways to express this as a sum or, okay, but whatever. And again, there is a reference here which is going a bit into these details. But the reality is, in the complicated graph I showed you before, there are many things which are not independent. So that doesn't really work to use this kind of formalism to derive uncertainties. So one of the options we have is this so-called Monte Carlo technique. Well, yesterday you heard about the Monte Carlo for the radiative transfer. That's a bit the same logic. Is are going to use random numbers to. Okay, let's restart from the beginning. So to do this, what you have to do first is to define the probability distribution function of each individual uncertainty. And that can be all sorts of distribution. That can be normal, log normal, rectangular, whatever, depending on what this uncertainty is. And what I mentioned before, their sensitivity coefficients, whether this parameter has a strong impact on the final results or maybe a very small one. And then you're going to take this complicated equation you saw before, and you are going to run it multiple times. And when I say multiple times, it can be thousands or millions of times if you want. And each time, for each of this uncertainty value, you are going to pick up a random number. So that's why it's called the Monte Carlo technique again. And that's going to tell you where to sample in these PDFs, the probability distribution functions. And you do this for all the uncertainties. You run it, you get a value of LW at the end. And you do it again, new series of random numbers, you get a new LW values, and so on. And at the end, you get maybe 10,000 of these LW values, and they will be distributed, generally as a log normal distribution, or as a normal distribution, sorry. And then you can define the mean values as the value of your parameter, and the weights of this distribution is going to give you the uncertainty. So that's a kind of brute force way of doing things, but that's probably one of the only one when you have so many uncertainty sources which are not independent. One thing to mention in this kind of context are this type A and type B uncertainties. That's the terminology of this metrology community. So a type A uncertainty is something you can derive from a series of measurements. Okay, so essentially the variance from the mean, so that you can experimentally make measurements and derive the uncertainty on this on the parameter. Type B, and that's taken from the GUM, the document I mentioned before. When the standard uncertainty is evaluated by scientific judgment based on all of the available information on the possible variability. Well, that's a bit, the pool of information may include previous measurement data, experience with or general knowledge of the behavior of and properties of relevant materials and instruments, manufacturer specifications, data provided in calibration certificates, and so on. So that's a bit more like a guess, if you want, in some way. It's not as grounded as measurement at a type A uncertainty. But many of the uncertainties we would have to include, in this complicated graph would be a type B uncertainty. And okay, when we did this and we applied this Monte Carlo technique to this Boussole data set, this is what we ended up for instance. And the vertical axis on this graph is the uncertainty in LW in percent, so from 3 to 5. So relative uncertainty in LW, and the number are the spectral bands. So 1, if I remember well, is something like 412. The 4 that you have here is probably the 490, and 9 is probably a band in the red, like 670, something like this. And the horizontal axis with the 20 measurement number in the data set. Yeah, that's because, when you run all this equation and you do the Monte Carlo technique, you do it for a specific situation. That means that's something you do for each and every measurement. Because that's something I should have mentioned before, by the way. Quite often, when people provide uncertainty for their measurement, it's just one number. They are telling you, with my profiler, I did some studies, and I can tell you that the uncertainty of the LW at 443 nanometer would be 5%. That's it. Okay. Whatever the situation is. With this technique, you are going to associate an uncertainty to each and every of your measurements. So that's the very powerful, that's why this technique is very powerful as well. So that's what you have here. It's just an example of 20 specific measurements of the Boussole buoy, may be taken at, during a day at different time of the day and over several days. And this is how the uncertainties are varying. And they vary because, sun zenith angle is not the same, the chlorophyll concentration is not the same, and so on. So all these individual uncertainties are different. And yeah, so that's one of the last thing, I guess, from the radiometry, the metrology part is that people in the metrology domain generally report their uncertainties either at what they call k equal 1 or k equal 2. And that's just about the fact that you consider 1 or 2 of the standard deviation in your uncertainty distribution. Okay. So if you want more on this, again, well, we had at this SLS in 2016, 2 lectures from Agnieszka Bialek. She's from the UK National Physical Labs. You can have a look to this. She's basically telling you about these kind of things, but in way more details. And again, the guide, the GUM document, which is the best source. Okay, so now we can have a look at the this uncertainty source, or from the instrument itself, from how it is deployed in the field, and then from how the quantities of interest, for instance, the remote sensing reflectance, are derived from the measurements. And so instrument-related uncertainty source, and that's when I'm giving the floor to Matt for a few minutes, because he's way more relevant than I am on this specific aspect. Okay.
Okay. Yeah. So yeah, so we're dealing with radiance and irradiance for the most part in this section, apparent optical properties. And so what we need to do is convert this radiant flux that we're getting, so that's the rate of energy transfer. And so you need to define like directional properties to that radiant flux. So radiance would be the radiant flux that is collected or emitted over a particular solid angle, like if you can imagine like a cone of collection. And irradiance is the amount of photon flux that's collected over a surface. And there's a few different methods for detecting this radiant flux. The photomultiplier tube is probably one of the earliest ones. It uses the photoelectric effect, where a photon will dislodge an electron. And the way the photomultiplier tube is designed, you've got a whole bunch of these diodes which collect these electrons that are emitted. They apply a big potential difference across them. And what we get is a cascade effect where that one electron becomes multiple electrons, so on across the photomultiplier tube. So these are very, very, very sensitive. And they're still widely in use today for very, very sensitive light measurement systems. We've also got semiconductors. So like the silicon photodiode, you're probably familiar with those. They're used in PAR sensors or your OCRs, like your multispectral radiant sensors. There's also diode arrays, which is essentially a whole bunch of these diodes put in a line or put in a two-dimensional array, and they're sensitive to light. And yeah. So with all of these different types of detectors, what we essentially have is a current, and we need to use that current and convert it into a voltage, and then later on perhaps digitize that so that we can get an actual record of the light that we're collecting. And so there's roughly two different ways to do that. There's a transimpedance amplifier, which is essentially you hook up the photodiode to it and you've got a gain resistor. You make the gain resistor higher and you've got more voltage coming out. The thing to note about the transimpedance amp is it's a continuous voltage output, so it's continually sampling the light that's getting detected by the photodiode. You can put a feedback capacitor in there. Can you see that mouse? Or is there a pointer? No? Yeah. Yeah, so you can add some smoothing. If you've got too much noise, you can add some smoothing. That slowers the response time, but essentially that's acting like a temporal low-pass filter over your measurements. So you're not going to resolve things very quickly if you do that. Transimpedance amplifiers are used in most of the PAR and multispectral sensors where the signal's pretty strong. And then the other type is the switched integrator amp. This type of topology is used in the hyperspectral sensors, where you've got like a diode array and you're reading all of these, essentially all of these pixels out. And what it's doing in this way is it's collecting current over a capacitor. And what you have is a discrete voltage at one particular point in time. And then you're sampling at a particular rate. Yeah, so you're building up current over a storage capacitor, and then when you're happy with the time or happy with the amount of current that you've collected, you flip the switch, then you can digitize that or take that voltage out and digitize it. So that time that you're collecting the current is commonly referred to as integration time. So you would come across that if you've used like hyper OCRs or Ramsey spectrometers, they've got the integration time. Yeah, and so once you've got this voltage, you need to then convert it into a digital count so that we can process it, store it, do things with it. And yeah, I just wanted to talk a little bit just to introduce you to ADC resolution. So if you've got a 2-bit resolution, you've got 4 counts, so 4 values. If you've got 10-bit resolution, you've got 1024 counts, so it's 2 to the power of the bit resolution. A lot of the sensors nowadays have 16-bit resolution, so you've got 65,000 counts, and you can resolve voltage levels within that, hopefully. But the ADC resolution doesn't necessarily equate to the actual measurement resolution. So if you had that transimpedance amp and you had a very high gain resistor and it's very noisy, you might just be resolving noise, but that's not so bad. You can deal with that. At least you're capturing the actual signal. Whereas if you had like if you only had 4 counts, you're kind of just not resolving anything. So yeah, we have to adapt these circuits to suit the types of measurements that we're using, the types of measurements we want to make. And that involves lots of design refinement, testing, characterizing its performance in a lab to try to simulate or see how these instruments would respond in nature. And then obviously perform lab calibrations as well. So there's a whole bunch of things to consider in instrument designs, the size and the shape. It might not be good to have a very huge light sensor if you're casting a shadow on the target you're meant to be measuring. Yeah, there's things to consider like heat dissipation. It would be lovely to have very high sensitivity electronics, but you're going to dissipate more heat. If you're in a battery style scenario, that's not a good thing. Yeah, so there's a whole bunch of things that go into instrument design, quality of the detectors, the linearity, how linear is that count response or that voltage response is to the photon flux. Yeah, lots of considerations there. So yeah, these are a few things that can and should be characterized when you're building a new sensor versus the linearity I mentioned. Secondly is a spectral calibration. So what wavelengths are you actually collecting? Have you got a filter in front of it, or is it a diode array which is using a diffraction grating, and that will have some type of finite spectral resolution? Immersion coefficients. So if you're using an irradiance sensor that you've calibrated in air and then you're putting it in water, the refractive index difference between the cosine collector and the medium you're in changes. So we need to apply immersion coefficients. So then that depends on the refractive index of the diffuser you're using. So you need to sort that out. You can't just change the material because it's got a better cosine response without then doing your immersion factor experiments. There's also temperature dependence to look at. So just because you've calibrated it at one particular temperature, does it hold when you actually go and use this instrument in the Arctic or leave it bake on the back of a deck in the tropics for a couple of hours before you then submerge it in the water? Can it handle that? There's also things like sensitivity polarization and stray light. So I'm getting probably the biggest, the most important thing, I guess, if you've kind of got a handle on all of these other things, is the radiometric calibration. So we need to compare the sensor's digital counts to that radiant flux standard. And there's a whole bunch of literature on this. This Ocean Optics protocols, this reference here is outdated now. I think the IOCCG is the custodian of this information. The documents have been updated, but I think the core of it is still captured here, where we're using a 1000 watt FVL lamp These things are old studio lights. They're becoming more and more obsolete now as LED technology comes. But these studio lights have been around for a long time. And what happens is when there's a batch of these made, NIST will get some and then burn them in for a certain amount of time. And then there's a certain percentage of these lamps that are really, really good and quite stable. Out of that fraction of those lamps that are stable, they then get compared with a standard. And then what happens is the standard is transferred onto the particular lamp. And then an instrument manufacturer can buy one of those lamps for about $3,000 Australian. And that's like a transfer standard, we would call that. So if you put a known highly accurate current through that, then NIST will give you a calibration certificate that this is the irradiance that this lamp is putting out at 50 centimeters within about 1%. Lamps degrade over time, so they've kind of got a feel that after about 50 hours, they're no longer within specification. If they're more than 1 year old, since they've been compared with the absolute standard, then they're no good as well. So you've got to buy one every year. Yeah. So the first configuration is the irradiance calibration. So you're just looking, your sensor is just looking directly at that lamp filament. And so you've got your coefficients that you've got from NIST. This is the irradiance at 50 centimeters. And then you can scale that by the actual distance that your sensor is away from the lamp. So you might not want to measure at 50, you might want to measure at 1 meter away. There's an uncertainty term here, delta F. Delta F is the uncertainty of like the distance between the glass, which you don't want to touch, because that'll change the calibration of the lamp, and the filament itself. So it's about 2.3-ish millimeters from memory, but there's a little bit of uncertainty there. And then how well can you measure that 50 centimeters or whatever? There's an uncertainty there. And so this is how you would scale your calibration coefficient according to these. For radiance, it's quite similar, except for you're illuminating a reflectance plaque. So this is a calibrated spectralone is one particular material. It's a very, very highly reflective material. It's like 99.8% reflective or something in certain wavelengths. When you buy one of these, you get the spectral reflectance, and then you kind of you multiply that by your measurements as well to calibrate that out. So there's a picture of it back here. So that's the reflectance plaque there. You can get all different sizes. So yeah, the idea is that you just point your radiance detector there. Obviously, radiance is looking at a cone over a solid angle, so you want to make sure that the field of view is completely within that target. Also, you want to have a large enough distance away from the lamp and the target as well. So that R in this case is probably about 1 meter. You need optics benches and alignment jigs and things like that. So there's some practical limitations. You also want to be as close as you can to get as much light as possible. It depends on how sensitive your sensor is. But yeah, the lamp calibration coefficients are E50. They're within 1% of NIST when less than 1 year old and less than 50 hours burn time. Yeah, the distance R between the plaque and the lamp surface. Hopefully you're within about 1 millimeter. Delta F, the distance between the filament and the lamp surface. Which part of the filament is it actually? Because it spirals around. So there's actually some of the filament at the back that's also illuminating. The filaments can sag as well. So there's a bit of uncertainty in that 2.3 millimeter measurement if you wanted to be pedantic. There's issues about the spectral and plaque reflectivity over time. Like it really likes absorbing grease from your hands. And then when you clean it, it still doesn't look perfect after you clean it. So there's some degradation there. And then how do you then characterize the reflectivity of that? So then you want to buy a couple and treat one very, very, very well. And then you might have an operational one. So you then swap between the two and treat one very carefully. Don't take it out in the field, things like that. I can't remember. I think it's like $5,000-ish. Yeah, but it depends on the size. You can get smaller ones cheaper. You can also get a 10% one, which is for other applications, but for this type of calibration, you want it as bright as possible. You want as much signal back. Yeah, also the power supply that you're running that lamp with has to be very, very stable and accurate. So you're drawing about 8 amps. Our power supply is specifically designed for radiometric calibrations. You can store like the lamp serial number and it logs the hours and that sort of thing. They were like 25 grand back when we bought them. I don't know what they would be now. But then they will drift in time as well. So you need to then get a shunt resistor, like a very high current resistor, and then be able to measure the voltage across it just to make sure that everything's working okay. Yeah. Okay. Yeah, the other thing about this is, so we've got calibration coefficients that are spectral, but then we need to know what the spectrum of our sensor is. And so for the hyper OCRs, the diode array spectrometers, over time, they can change. The band centers can drift over time. So then before we calibrate, especially if the sensor's a few years old, you want to look at like an emission line source, and then put your sensor in front of an emission line source to see if the lines have spread out over time. Because then the error propagates through and can lead up to errors of like 6%, 6 to 10% in the red. So if you've got an old spectrometer that you haven't done the emission line test on, you could have like, 6 to 10% errors in the red. So this is the type of spectrum that you get from a lamp. It's kind of like your typical incandescent lamp response. But then you can see that the spectrum in nature is actually the opposite. So you got lots more blue, typically less red, but you're calibrating to something that's the opposite, which is not ideal, but it's what we have to live with for now until LED technology gets stable enough, but I don't know if it ever will. But the lamps tried and tested. Yeah. Do you want to take over?
Yeah, sure.
Yep. Yeah. There's some slides showing you that for hyper OCRs. Yeah, you have to, well, to minimize your uncertainty, the manufacturer would be calibrating them and characterizing them over the temperature ranges that you'd be using in the environment. That typically hasn't really happened. But yeah, it's been identified and there's literature on it. And there's some references on following slides that show you. But ideally, if you take your sensor back to get calibrated, you could then potentially ask them, hey, my typical temperatures are this. Yeah. Or you could pay for 3 different calibrations. Say, please put it in the fridge or whatever, do one at 15, 25, and 35C, and then you can linearly interpolate the calibration coefficients. So that's what we do with ours. Ever since we did an experiment with David in 2016 and took our Dalek radiometers out there, compared them with some of the others, and then we then took them in a lab and then did the different temperatures and did that, and we were like, wow, up to half a percent per C. Yeah, it's in anyway. Spoiler alert. Yep. Yeah, sure.
Oh, you want to? Thank you, Matt. Thanks a lot. Was it okay? This one. Yep. Yeah. Yep. Nope. There is something I didn't mention on this one actually, and I just selected one example just for the purpose of this slide. But on this one, clearly, there was probably a change in the above water incoming irradiance, which is making this, because normally, yes, that should, this noise, but there was a noise, but the overall slope should be like this, and it's not. So there is probably, that's one thing that I did not mention into this. Maybe that's in the next few slides, I don't remember. Of course, before doing any of this extrapolation or whatever, you have to normalize for any change in the above surface irradiance, which would, yeah, on this one, no, because it's from the Tethys, actually. So there is no ship here, it's for sure, but yeah, okay, it's okay. Yep, that answer to your question, or yeah, yes, yes, yeah. Oh, yes, yes. Oh, okay, yeah. I'm getting into this later, yeah. But that's, yeah, yeah, that's the difficult part. Okay. Yeah, so Matt was on this slide. So indeed, it's actually quite a significant problem we have in this, in all the marine optics for many, many years. But as Matt said, there was some hope that new calibration source using diode arrays and so on will have a spectral composition much closer to what it is in the real environment. And that should, again, that would be a way to decrease uncertainties. Okay, when you have been doing all these things in the lab, all these characterization experiments, calibration, and so on, uh, manufacturers or yourself, if you have a lab to do this, you do your best, and but then generally a good way, a good idea to go and check this in the field before you deploy in your instrument. Well, depending, if you have just one instrument, that's okay. But if you have a system with multiple sensors and so on, it might be a good idea to check whether they all tell you the same and they're all consistent. So that's just one example of what we did as well for this boussole system, where we had quite a number of sensors. And we built this bench that you see on this photo here. We have all the sensors properly installed on it, and we went on a relatively high altitude place, and we collect measurements basically from the early morning to the midday. So we have the sun altitude changing over the time, and then we compare the different instruments. So all of these plots on the right are for a given wavelength, and they compare, for instance, here it's the comparison of two downward irradiance sensors. Yeah, that's what it is for the 7 wavelengths we have. Okay, in that case, you can see, well, they all compare very well, so you're happy. It's not always like this. Sometimes, oh gosh, you have something like this. So clearly there is one of the sensor which is not giving you the same answer than the other one. That doesn't necessarily tell you which one is correct. So sometimes you need to make multiple comparison to get to this idea. Anyway, but that's, I guess the point here is, yeah, if you have a way to make this intercomparison of your sensor, that's a good quality check. One of the important parameter that Matt mentioned and which needs some characterization as well is what we call the cosine response for the irradiance sensors. which is telling you that, the response is going to change with the incident angle of the radiance coming into this diffuser. So it all depends again on the material and the shape you give to this sensor and whether you are going to put this in air or in water. And ideally, you want to have a cosine response like the one you have on this plot on the top right. But then you can, check this in the lab and derive some kind of uncertainty or corrections for the non-perfect cosine response of your sensor. And this is the experiment that Matt mentioned we did some years ago now. That was in northern Queensland. So we went on a platform there where there is, and we intercompared many sort of different instruments. So the picture you have on the left, they are all irradiance sensors looking at the downward sun irradiance. And then on the right side is the comparison as a function of the sun zenith angle. So from the nearly zero, we were there at the time of the year where indeed you can have the sun just above your head up to nearly 60, 70 degrees early in the morning or in the evening. And what you have here is the error in the angular response by comparing these different instruments. So you recognize hyper-OCR, Ramses, UCMO is an instrument, and DALEC are instrument developed by Matt company and the DALEC as well. And well, you can see this response is quite variable among different instruments. So if you consider relatively low sun zenith angle, that's not too bad. It's generally within 5%, but it can reach quite high value. So that's all depending on the design of the instruments and whether maybe the collector has been aging, if it's an instrument which is a bit old and has not been recharacterized and so on. Yep. Oh, yeah. As well. Yep. You can actually see those points. I don't line up. Yeah, that's one thing we try to characterize with this experiment as well. Oops, sorry. Where this temperature dependence on the hyperspectral sensors. And so what you have on this plot is just for 3 different sensors. So the top row is for the Ramses, so from the German company Trios. Then you have the hyper-OCR from Seaburn Atlantic. And the one on the bottom is the DALEC developed by CQ Marine Optics, the company that Matt is running. And so, if you look at the middle column, you have the relative difference in percent of the calibration as a function of wavelength. And the blue curve is, whoops, that's a sensitive screen. So the blue curve is for calibration made at low temperature, and the orange one at a high temperature. And you can clearly see that, within plus or minus 5%, more or less, it can reach sometimes higher values. And it's represented now on the right column. It's the normalized correction factor in some way that you would have to apply as a function of temperature from 20 to 35 degrees. So yeah, you can clearly see there is a trend and a change in the calibration coefficient as a function of temperature. So if you want to apply this, of course, that means you need to have a sensor telling you the temperature in your instrument. Yeah, and you may take a bunch of hyper-OCR instruments and do the same intercomparison, and you would again have a spread of values because they are all the same. But as Matt said, there are small manufacturing differences, and they might not have been calibrating exactly the same way. So yeah, so there is a lot going on at the moment, in many many labs to make this inter-comparison exercise, because that's where you learn quite a lot about your instruments and whether they perform well or maybe they are completely off as compared to others. And that's a way as well to encourage, I would say, people to look at this a bit more carefully. Because, there are quite often this idea that you get an instrument from a very well-renowned manufacturer, they have calibrated it and they think they have done everything they can to, but, there is a bit more than just this, and you realize it when you do this kind of detailed experiment. Now, we have barely scratched the surface of this topic, but as you can see, there are plenty of source of uncertainties just with the instrument itself. This slide is saying, well, do not panic. Even if I may have said a few things that might look a bit critical about manufacturers, but they generally, they do, the right thing. I guess the message is just try to educate yourself on these things. So at least and sometimes you will see something in your data and you can say, okay, I think I have a problem with maybe the temperature correction, or maybe I have some straylight in my instrument. So you can figure out whether there are some issues in your instruments, in your data. A good way to improve this is to talk with these manufacturers as well, at least when they listen. Some don't listen necessarily very well, but okay. And radiometric protocol documents are to be updated to include new sensors. Yeah, that's with a question mark. I'm not exactly sure what I want to say with this, by the way. Yeah. Okay, well, let's forget about this. Okay, add sensible error bars on instrument and move on. You can, of course, do this and try not to get too much into the details, but anyway. And in some way, some people would say the bigger the error bars, the easier disparate data sets can be said to agree, but that's okay. That's a bit kidding. Yeah. Okay, that was for the instrument only. Let's check. Okay. Now, assuming you have done everything you can, you have a perfect instrument, but then you are going to deploy it in the field. And one point I really want to make is what makes radiometry measurements a bit special, because sometimes because we have quite strict protocols to do this, and quite often when I've been on cruises with a crew or other scientists who were not used to have optics people on board, and they really sometimes think you are really a pain, because you ask for all sort of things, all sort of constraints on how you are going to put the ship, and the people say, well, what? Okay, maybe, but why do you care? And very often I use this example of, what would you think of someone who wants to measure temperature, the water temperature, as a nice sensors on the frame and deploy it, and deploy this just at the exhaust of the ship cooling system. But it's just really stupid, Don't do this, of course. You're measuring the temperature of the exhaust, not the temperature of the water that you want. But actually, if you take an optical sensor or PAR sensor, you put this on a big rosette, and you deploy it just right a few meters from the ship with the sun on the back, you're doing the same thing, basically. You're measuring something which has absolutely no meaning, because it's just completely perturbed. So I guess, and the point is, why is this? Is because, okay, you have probably seen many, very often this kind of graph, which are supposed to explain what ocean color is with the sunlight coming in, being diffused, scattered, and absorbed, and so on, and generating the signal. But okay, that's theoretical. Then to measure this, you need a platform. That might be a ship. Sometimes, there might be some clouds in the atmosphere and so on. So, but the key point is that the value of a radiometric quantity like LU or ED measurements at any given point in the water column is instantaneously results from the interaction of the light field with the atmosphere and the water over a very large domain around yourself. That's not the case when you measure temperature or salinity with a sensor. That's what it is at the given point. Whether the temperature 10 meters away is 1 degree higher, you don't care. You measure things. With radiometry, it's different. The value you have here is just the integration of a very large volume of atmosphere and oceans. That's why it's making things a bit complicated, and that's why it's making the protocol and the precaution you have to take very important. So environment and deployment related uncertainty source. So what to consider? Well, generally, you have to consider the weather, of course. If the sky is cloud-free, overcast, or maybe with broken clouds. So, and even if it's cloud-free, how clear this is. You might have an extremely clear atmosphere with nearly no aerosols, or you might have some haze, and you will have a kind of blue, milky blue sky. That's making a difference. What about the sea surface? Is it rough? Do you have white caps, significant sea spray? And, but again, the reaction we'll have to this and saying, oh, I'm not doing any measurements, that's not going to work. Or yes, I'm going to do measurement, might depend, of course, on what you want to do with this data. If you want the very best data with the very lowest uncertainty, or maybe, you're doing something where you can accept relatively larger uncertainties, the decision you will make as a function of the weather is going to be a bit different. Water, how clear or turbid the water is. Can I suspect strong vertical stratification if I am maybe close to a river mouth with some fresh water coming in? And how homogeneous the waters are around the place I'm going to sample. So that might define how you're going to deploy your instrument. Precaution you might have to take with the boat, because the boat is perturbing the environment. You might completely mix. You might have come with a big boat and mixed all the water, and then you make a measurement, and you get something. But actually, maybe that's not what your satellite is going to tell you, because actually, if you would not have been coming and mixing everything, the reflectance could be a bit different. So that's the kind of thing you have to keep in mind as well. And of course, the platform and the deployment. So whether you deploy your instrument from a huge research vessel or from a small dinghy, that's of course make a big difference in terms of shading and water movement and so on. Can I move my instrument far enough from the ship to avoid the shade? Very important point generally, where can I install the deck reference for the above water irradiance? It's very often that's a difficult thing. It looks like, okay, just put it away from, but sometimes the captain won't allow you to go on that very high place on the ship because it's risky, or maybe there is just no way to find any place on the boat. So that's the thing you need to consider. Can I easily communicate with the bridge? Well, that's when you deploy something, and you need to tell them to move a bit the ship away from the forward, or to turn the ship to have the sun in the right direction, and so on. Do you have enough help on the deck? All sort of things like this. So that's, and finally, the instruments. Okay, other from what we said that has to be done in the lab before. Maybe I forgot to clean the optical surface, so I should keep this in mind. Was the instrument properly stored? You don't want, as Matt said, leave it on the deck for hours under a big sun. It's going to warm, and then you don't know what the response is going to be. You might even damage your instrument. Did you check all your cables and connectors? So, and the list goes on of all these things that you have to consider. And generally, well, there are now, documents and publication and everything that you need to know about this on the web. There is in particular these references I have put on the bottom of this slide, which are coming from an intercomparison exercise that the European Space Agency has been funding for quite a number of years now. And well, this one is just to it's a slide just to summarize the different ways to get to this AOPs, and in particular to the water-leaving radiance. So on the left is what I have illustrated a bit before with this buoy, where you have measurement at fixed depths in the water. This one in the middle is the classical way of deploying free-falling systems, where you get a profile. This one is for the above water measurements on a platform or from a ship as well. So we look at the sea. And this last one on the right side is a slightly different techniques, which has not been very widely used, but it's quite interesting. It's called the sky blocked. So it's again, the idea is to measure from above the surface, but very close to the surface. And with this little cone, which is blocking the skylights, what's supposed to block the skylight, you don't have this reflection of the skylight. So normally you directly measure the LW from the surface. The point is, okay, we're not going to go through, because you can imagine if you try to derive LW with these different sort of techniques, the kind of processing and the kind of uncertainties associated to this are going to be, of course, quite different. And that's what is a bit summarized on this slide. So you have the list, from 0 to 7 or to 4 of the main source of uncertainties for these different techniques. You always have the radiometer itself. That's what we discussed a bit before. Then you have the uncertain, whoops, should not do this. Uncertainty on the vertical extrapolation for this one. For this one, it's about correcting for the reflected skylight and so on. And again, that's all relatively well described in this paper. Okay. I think I have two illustrations of the effect of the platform on your measurements, and this example it's a paper from Hooker and Morel in GAOT 2003. They were doing some intercomparison of deriving reflectance from in-water systems and above water systems, but they were as well looking at when you do the above water system, you have your sensors somewhere on the ship looking at the water, and they were looking at the effect of the geometry of the problem, basically. Meaning, okay, you're supposed to look at a given angle, but at the sea. But then you have waves and swell, and whether the orientation of the ship with respect to the main direction of the swell, and these kind of things, and how how far from the ship the instrument was pointing, because generally you try to be on the bow of the ship, for instance, and so you don't have the massive ship too close to where you're looking at. Sometimes you just can't, so you have to put your instrument on the side of the ship, depending on the configuration. And then you want to see whether if you really need to look perpendicular to the ship, or what's happening if maybe you look a bit closer to the ship. Or they had to look to all these kind of things. And they have managed to, by comparing with the in-water system, to derive some errors or uncertainties. In that case, that's on the this small r in the near-infrared, which is the coefficients you use to correct for the sky radiance. And they were showing that depending on all these geometrical parameters, actually the coefficient would change, and would change because of for instance, on the top, on the bottom left plot, that's about the angle between the sensor and the swell directions, and you can see the impact. And the other one here is the angle by looking a bit more close to the ship. But anyway, that's an interesting paper in this respect, because it clearly shows that the impact of relatively small change in the setup you have when you deploy your instrument, you install it on the ship. So that's really something you have to each time you do a deployment, you really have to think to this and try to get a sense of what sort of configuration you have to use to minimize these issues and these uncertainties. Another example of this is when it's an experiment that was done from this big tower, which is installed in the Adriatic Sea, close to Venice. And while they were doing a similar thing, but you see they have this long arm coming out of the platform. And so they can put the sensor further and further away from the platform and look at whether there is any change in what they measure. And on the plot on the right, you clearly see the relative percent difference, which can be quite huge as a function of the distance from the platform. And when they come too close, of course, there was a big perturbation and the relative percent difference can be significant. Okay. Again, that was kind of a quick overview of this, and I guess that's what we generally describe as the protocol. The protocol you have to follow to get good measurements. What's important to keep in mind is this protocol are not to be taken as a frozen thing. You know, I take the document, they say this is how you do this and this and this and that. Okay, there are probably a number of things in those protocol documents which are applying to most of the situations, but many of them are actually going to be specific to your measurement platform, your instrument, and what you want to do. And that's when, then, if you want to be sure that you don't blindly apply a protocol which, or maybe is not completely adapted to what you want to do, you need to understand why the protocol is telling this and that. And maybe, okay, the protocol is telling me that, but I know that in my situation, I just can forget about this. It's not important. Or maybe, yes, that's the very important point I have to and I cannot tell you which one it is. It's all depending on where you go, what sort of water you are sampling, instrument, and so on, this type of ship. So yeah, keep this in mind. It's protocols have to be taken with a pinch of salt in some way, that you have to adapt them as well to your measurement setup. Okay, to conclude, the third and important source of uncertainty is, okay, when you have been perfect instruments, you are doing your best at sea, and you have excellent data, then you need to process all that stuff to derive your KDs, reflectance, and so on. And again, just a few quick examples to illustrate this. First thing you might have to do is what we call a data reduction, because some instruments are going to give you a lot of measurements, but maybe quite a lot of the measurements just have to be discarded because they were not collected in the ideal condition, and you have to select in this the good part. Now that's one example with this DALEC sensor that we have been using quite a bit now. So it's a sensor which is collecting measurements from above water, and you can install it somewhere on the ship and start it, and it's doing its own measurements. It's orienting itself with respect to the sun. And at the end, you may end up with a full record over a given day. That's what is illustrated on this plot. And you have the black curve is the downward irradiance. So you clearly see the daily cycle with the sun coming up in the sky. The green curve is for the LT, so that's the measurement you get from the sea. And LS is the measurement of the sky, radiance. Okay, well, not going to comment this in detail, but you can see that probably immediately understand from a record like this, there are some sections which are quite noisy. We don't want this. Maybe there were some clouds. There are sections where the signal looks very stable. So, okay, so that's the first thing you might have to do with this kind of systems is to go into this and select just the relevant data for your application. Another thing you will very often have to do You remember I said that it's always kind of difficult to find the right place on the ship to put your ES sensor, so the downward sun radiance. But even if you find the right place, the ship is generally going to move. And even if your instrument is on a gimbal, generally that doesn't work very well. So the instrument is always going to move. So even if the sky is perfectly stable, nothing is changing, your record is going to be like this. And just because your sensor, which is a planar sensor, is going to be tilted and receiving the sunlight from a slight angle, so you have a change. But we don't want to take this into account, of course. It's just because the ship is moving. So that's an example here. The different colors are for different wavelengths. And the vertical axis, well, it's called pressure, but actually it's time for this one. So that's a record of ES, which was done during a profiling, a profiling system was going on in water. And during that time, the ES was recorded, and it was, with all this fluctuation. That's a day with a perfectly clear sky, but then the ship was probably moving quite a bit. So what do you do with this? Well, you need to figure out what to do. Maybe you keep only the data which are with a very small tilt of maybe 1 degree, and you play with this. Maybe you may make a fit into this. Again, that's your decision, that's your data, that you want to do something with it. You need to, but then that's an important step you have to do, because you are going to use this to normalize the in-water data, and you don't want to normalize for the movement of the ship, of course. The other thing which is a significant source of uncertainty as well is this extrapolation to the 0- system, depth, sorry. And the example here on the left side is again from the Boussole buoy, where we had only one measurement at 4 meters and one measurement at 9. Of course, that's only two depths. You cannot do anything else than just calculate the K coefficient between the two depths and use it to extrapolate to the surface. You don't have any other way to do it. Well, I mean, and that's what is illustrated on these plots in the blue on the left and in the red. We knew that in the blue that was probably not too bad because the K coefficient are not changing too much close to the surface. But we knew that doing this in the red was probably quite bad because the K coefficients are changing quickly at the surface. And that's what is illustrated here. So what we did, actually, we went to radiative transfer and we calculated with we ran a number of simulations of this kind of wavelengths. And that was giving us the shape that the upwelling radiance profile would have normally in such waters. And we could apply that shape to our two measurements and make a better extrapolation to the surface by doing this. And we checked it, and that's what is on the right side, by comparing to what we would get from an in-water profiler, with which you have less of this issue because you get measurement much closer to the surface. So the extrapolation is less uncertain. And then you have the comparison on this thing. It's on the EU 0- spectrum, and with different techniques of extrapolation, and the black one, which is the true one from the in-water profiler. So that was showing us that we were doing quite a good job with this correction. But this is, and those who advocate for doing the measurement from above the surface very often take this example to say, look, your extrapolation is always kind of very uncertain, so that's much better to do it above the surface. Okay. And the people who prefer to do the in-water stuff will tell the people doing the above water stuff that the correction for the skylight is a very difficult thing to do. And at the end, the both are true actually. And if you do a good job in comparing these two techniques, and if you apply the two techniques properly, you generally get the same thing actually. Can skip this one. Well, again, that's the last example for this problem of extrapolating to 0-. In that case, it's a system called the TETIS that we deployed for a few years, which has been decommissioned now. But basically, it's a profiling system. It's anchored on the bottom, and it's equipped with a number of sensors, including radiometers. But in that case, we don't have any above water reference first. And the second thing is the LU sensor is at the bottom of this relatively big cage. So the shallowest value we have for the measurements are probably at 2 meters. So again, we have all sorts of things to consider with how we are going to extrapolate and calculate this LU 0 minus again, without a surface reference and with the shallowest measurement at about 2 meters. So we did this with Matt as well, and we tested a number of methods. I don't go into the detail. That's what you have with this RS 1, 2, 3, 4, 5 here, and it's more or less explained. But then we were trying different ways of doing this, but we didn't have any other measurement to tell us which one was the right one, actually. So I made the decision to look at these 5 techniques to calculate the LU 0 minus, to look at all sort of clear sky days and look at the distribution of the values we were getting. And considering that the method which would give us the distribution the closest to a normal distribution would be probably the best one. That's kind of subjective, but anyway, that's how we decided to use one of these different techniques. Okay. Okay, so that's it for this part. There is a very interesting resource. I have put the link here. It's on the Ocean Color website, the NASA Ocean Color website. It's a number of presentations from a workshop we had some time ago, but a lot of this is still already valid. And it was a workshop about, how do we do all this processing and how do the results compare? And so all these presentations you have here are from different groups doing things a bit differently. So that's a very good source of information on I would say, the variability you may have in the way to derive AOPs from different sort of radiometers. Again, coming back to the importance of comparing data sets to having different instruments on the same cruise, so that can give you a bit more confidence about what you get at the end. So example on the left slide here is from comparing reflectance, remote sensing reflectance from the Boussole buoy on the vertical axis and from the in-water profiler that we were deploying on the cruise on the horizontal axis. So yeah, it's going relatively well. And the other one on the right side is comparing an Hyper Pro, so this Atlantic seabird system, with the CEOPS, which is another free-falling system from the biospherical company. And well, again, we were deploying the two at the same time on the ship, and we managed to get this very good comparison. And the last one is about comparing again the remote sensing reflectance with okay, on the horizontal axis, it's from the CEOPS, so this in-water profiling system. Vertical axis is the DALEC, so the one you saw a bit before. It's an above water system, so we were doing the measurements simultaneously as well. And while the 6 panels on this figure correspond to different ways, again, of correcting for the skylight reflection in the above water system. As you can see, that generates a bit of difference, and in particular for the red bands, that's where the thing is the comparison is less obvious. Okay, well, I can skip this one, that's the same. And well, I think John talked about this yesterday. The other thing you can do then, if you have radiometers and IOP instrument at the same time on your cruise, you can try to do this optical closure. That's a very good way to reassure yourself that your data set is consistent. Of course, you need to do it well if you want it to be useful, because as was reminded by John yesterday, if your IOPs if all your data set is fine, and you try to do one of these closure experiment, but maybe you mishandle whether it's hydrolyte or whatever is your radiative transfer code, you might not get a closure at the end, which is not because the data are wrong, but because you have been wrongly used the radiative transfer. So just, yeah, you need to be sure that you are doing the right thing. But if you manage your radiative transfer code well, you know it well, and you know that you are doing the right thing, adding your measured IOPs, going through this, deriving the radiometric quantities and AOPs, and comparing to the AOPs you have derived from your measurements is a very good way to get some confidence that everything is consistent. And again, the plot you have on this slide is this kind of exercise we did for this TETIS profiling system we had in the water. And the kind of scatter of the data in this is actually quite good for a system like this. You might get a much better closure and much less scatter of the data if you have a system where you control much better the way you do the extrapolation and everything. But anyway, and you don't need sorry. Yeah, I don't know. We don't really know. There are two different deployments. And yeah, that's the kind of thing sometimes you try to figure out. But yeah. And the conditions were quite similar. Unless yeah, I think maybe 2020, just try to remember, that was a summer deployment. So we go a bit in the lower values in the clearer water, so the lower values for the red bands. Yeah, and sorry, this is merging all wavelengths. So what we have here, these very low values are for the red bands, and it's in clear waters the values are always very small, so it's kind of difficult to get a perfect closure. But what you need for this is just total absorption, okay, and total scattering and the phase function. That's all you need to make these radiative transfer calculations, and the boundary conditions, of course. And of course, the phase function, we don't have generally measurement of the phase function. That's the difficult part. So you have to select something that you think is going to be relevant for your situation. So in that case, I think we used the chlorophyll variable phase function of Morel et al. 2002. Okay. Yeah. Let's see here. Oh, yes. Yeah, one thing is actually one of the most important parameters in the VSF for this kind of calculation is the ratio of the backscattering to total scattering. And so I think if you have some measurement of backscattering with your IOPs and total scattering from an ACS, for instance, you can have the measurement of this ratio of backscattering to total scattering, and you can use this to specify a VSF which has this same ratio. Or at least you can constrain the system, even if the entire shape of the VSF is not correct, because we don't exactly know what it is. At least if you get this ratio of backscattering to total scattering right, you're on the good track. Okay, and I think I'm nearly at the conclusion. So it's just giving you a few examples of programs which have been addressing this uncertainty issue for quite a while. So this is this FRM for SOC.org. So that means fiducial reference measurement for satellite ocean color. That's a program that has been funded by ESA. And there is a second stage, which is FRM for SOC number 2. And that's all about these things, intercomparison exercise, protocols, how to derive uncertainty, and so on. So if you go, there is a special issue of remote sensing that was published 2021, I think. There are probably quite a few other that will come in the next few years. Just a parenthesis, yeah, there is this FRM, fiducial reference measurement terminology, which has been introduced a few years ago. It's basically when well, that's my interpretation at least, when space agencies like ESA, they had and they still have these validation programs where they try to get validation data from as many people as they can from the community, okay? And they build database for this and they try to use it to validate their products. The thing is, at some point they realize that, well, maybe, okay, that's fine, they get all sorts of data, but they are relatively no idea of the quality of the data, or they would have just to rely on what the people were telling them. Yeah, this is my very good data, and just take it. And so they started to say, okay, we should probably have a way to ourselves have a better idea of whether the data quality, the quality of the data we are provided is good enough to do the validation work. So they came with this fiducial reference measurement concept, which is supposed to mean a measurement coming with as comprehensive as possible an uncertainty budget. So, and of course, an uncertainty budget having been derived following some very specific protocols and blah, blah, blah. So at least if they have this, they can consider that they are ingesting data of the required quality for their validation work. Another example of a program doing this at the UK National Physics Lab, which has always had a very strong role in all these programs, so the UK NPL. And of course, the Ocean Color Web and the IOCCG website, which are where you can find all these protocol documents. It's, you know, basically everything you need to really understand all that stuff is on these two websites. Yeah, I think that's it for today. Just in time. Thank you.